the last class, we have derived the expression for the Helmholtz free energy density for a liquid solution, and we will take from that expression today and go on to describe the different phase behavior of a liquid solution, and then we can extend that to a polymer solution. So, just to recall what we have derived using the lattice model of liquid solutions that contains essentially two species, a solute and a solvent. Both are assumed to have the same volume, same as the lattice cell volume, and they are essentially occupying positions on a lattice rather than moving on a three-dimensional volume. So, for this case, we have derived that the Helmholtz free energy is given as we can identify some terms here and assign some meaning to them, and those meanings will then make some sense, and using those meanings we will develop the model for polymer solutions. So, I will do, when I am assigning this particular meaning to these terms, it is not very rigorous because it is anyway a mean field approximation, and we cannot really decouple terms the way I am proposing it to, but it really helps us understand that what kind of contributions come into the free energy of a solute solvent system in general. So, the first term we can associate to some entropy of solute, because phi is its volume fraction. If you go back in the derivation, we had a logarithmic of the number of microstates, and from there we have got this particular term in this expression. The second term, for the same reason, is the entropy of solvent, and the last term is the interaction, that is apart from entropy, between solute and solvent. I will use the word effective interaction here, just to recall you that chi came from an effective energy delta epsilon, and delta epsilon was something like epsilon pp plus epsilon ss minus 2 epsilon ps. That is, it depends on not only the solute interactions, but also solute solvent and solvent solvent interactions. So, it is like an effective interaction between the solute and solvent. Okay. So, with this, what we have also discussed is this function happens to be symmetric around phi equal to 1 by 2 And of course, this is what will happen for a phase separation. For no phase separation, we should have a behavior like this. In terms of chi, if chi is higher than chi c, some critical value, we will have phase separation, and when chi is less than the critical value, we will have a homogeneous system. Okay. So, the larger value of chi refers to the poor solvent conditions. The solvent, larger value of chi means poorer solvent, lower values, particularly negative values, would mean a good solvent that will tend to form a homogeneous solution of solute and solvent. Okay. So, now let us work on this expression. We have also said that the advantage of symmetric F is we can draw a common tangent and solve F prime is equal to 0 for the binodal rather than solving a more complicated equation. So, let us go ahead and look at how the derivatives of this look like, and then we can find the binodal, spinodal and critical point for this system. So, I reproduce my function here. So, if I take the first derivative f prime is tau f by dou phi, that is equal to kbt by Vc 1 plus ln of phi minus 1 minus ln of 1 minus phi So, in the first minus 1 comes because we take 1 minus phi multiplied by the derivative of ln, that is 1 by 1 minus phi with a negative sign. So, that is how we got a minus there. And the second term is simply we keep ln of 1 minus phi and take a derivative of 1 minus phi, that is also minus 1. Plus chi multiplied by 1 minus 2 phi. And so, for binodal line, or the coexistence curve, in this particular case what we have is dou f by dou phi is equal to 0. So, if I call chi b to indicate the binodal line, by solving that equation I had, it is chi b into 1 minus 2 phi plus ln of phi by 1 minus phi is equal to 0, that is minus 1 by 1 minus 2 phi ln of phi by 1 minus phi. Okay. Now, we can go ahead and find the spinodal by simply looking at the second derivative of f. So, we already have found the first derivative. So, f prime is ln phi by 1 minus phi plus chi 1 minus 2 phi, and so if I am interested in the second derivative, that is, then that will be equal to one by phi minus of 1 by 1 minus phi, the minus will cancel, minus 2 chi. So, if I want to get the expression for the spinodal, line, then it has to be given by f double prime is equal to 0, which give me the expression if I represent chi s as the function value of solvent quality for spinodal line, that has to be 1 by phi plus 1 by 1 minus phi, the whole thing divided by 2. And then if I want to find the value of the critical point, I have to find the third derivative. So let us go ahead and try to find the third derivative. So this has to be minus 1 by phi square plus 1 by 1 minus phi square. There is a cancellation of minus signs. This has to be equal to 0 at critical point. If I solve the equation for the third derivative, what I will have is, let us say 1 by phi c is a value of the volume fraction at critical point, then this has to be equal to 1 minus phi c squared. This gives me 1 minus phi c by phi c as plus or minus 1. You can solve for minus 1 and find out that phi c will not be in the range of 0 to 1. So we take a value of plus 1. So 1 minus phi c is equal to phi c, and that will be phi c equal to 1 by 2 at critical point. If I want to know the value of chi at the critical point, I can put this value of phi in the expression for spinodal or in the expression for binodal, because both binodals and spinodals do merge at the critical point. So let us say I am computing the chi s for phi value as phi c, then this will be equal to 1 by 2, 1 by phi is 2, 1 by 1 minus phi is also 2. So this has to be equal to 2. You can try plugging in also in the earlier equation, and you should essentially get the same value. But the problem here is that in this particular case you get a 0 by 0 kind of a term. So you have to take a limit and use L'Hopital's rule if you are going by the binodal. But essentially both of you should give you the same result, that the solvent quality at critical point is equal to 1 by 2. So putting all these ideas together, what we then have is the following phase diagram that I will draw here. So we have chi versus phi. So of course for chi less than chi c, there is no phase separation. Phase separation only occurs beyond chi equal to chi c. This point, by the way, is phi c equal to 1 by 2, and this is chi c is equal to 2. This curve is my coexistence curve. This I get by solving the equation for the binodal. Inside this So, this is my binodal. Inside this we will have a curve for the spinodal chi s phi, and both of them of course will merge for the at the critical point. So, just the way we have defined the metastable and unstable regions earlier, on this side and on this side we now have a metastable region, and in the middle this region is my unstable region, and of course outside the envelope we do not have any phase separation that is occurring. So, this we have discussed for liquid solution. Now, I will tell you like how can we extend these ideas to a polymer solution. So, a more rigorous way of doing it is to try to get the actual number of a polymer configuration on the lattice, but it turns out to be somewhat complicated and in maths. So, we will first describe a purely intuitive approach and try to see like how does it captures the behavior of polymer solution. It turns out that even by doing a more rigorous mathematics will give you the same result. So, I want to start with the f that we have derived and now recall in this particular case of liquid solutions we have identified these three terms as my solute entropy, solvent entropy and the solute solvent interaction. And now we note that if I now want to put a polymer chain there, the first approximation that goes wrong is the approximation that the solute and solvent are of the same volume. Of course, the approximation was not very correct even for a simple liquid solution, but at least they were of a similar size or similar order of magnitude of size. But if we have a polymer chain present in say water, then of course the size of a polymer chain is nowhere comparable to the size of a water molecule. It's of course the polymer chain is much larger compared to the water molecule. Now, the other thing that we have to keep in mind is the solute molecules can then go anywhere in the lattice with relative ease. In the case of a polymer molecule, now they have to move together. So, when all the ingredients or all the beads, all the segments of a polymer chain are moving together compared to the case when the solute molecules, the small ones are moving separately inside a lattice, what you can note is that the entropy of a connected polymer chain where it is formed by connecting these individual segments or beads should be much smaller compared to the entropy of small molecules. Okay. So, other way to think about it is and I will build on this representation in the next lecture. is, if for example you have solute molecules like these on the lattice and remaining positions are occupied by the solvent molecules, they will have much larger entropy compared to the case when these solute molecules I have drawn rather represent a bead or a segment of a polymer chain. So, in that case, now these molecules, let us say you had 5 molecules as here, now they have to move together. So, the number of configurations is much lesser than the number of configurations that we had in the case of a liquid solution, because now the segments of a polymer chain cannot move anywhere. The reason why we have chosen segments as the unit is because we can imagine the segments at least may have the volume of an order of magnitude similar to a water molecule. We can always decompose a large polymer chain into smaller segments. We can have say 1000 segments or 10,000 segments. Each of those segments then have a volume similar to a solvent molecule. So, in that context, instead of putting an entire polymer chain on a given cell, I will now put a segment in a given cell, and now we will perform a random walk on a lattice, just like we have discussed in the random walk models we have done earlier in the course, right. So, the main idea is that once the segments are connected and they are moving on a lattice, now this happens with a much lower entropy than compared to the case where segments would not have been connected, or rather speaking, we can say that the solute were smaller in size or comparable to water molecules or solvent molecules. So, what it turns out then is, if I want to go from this model, a liquid solution model, to a polymer solution model, all I have to do is simply divide the first term by n, because the polymer entropy is very reduced, very less compared to the solvent entropy, where n is the number of segments of polymer chain. In fact, we can pretty much also drop the first term, because polymer entropy in any case will be very smaller compared to the entropy of solvent molecules. So, we will start from this point and then discuss the phase behavior in the case of a polymer solution. Thank you.